So we're ready for these terms. So we've got all these different um, concentration terms, and the hard part for this chapter is you have to keep up with what is the solute, what is the solution, and what is the solvent. So when they give you a problem, you're going to have to identify these parts, and then you have to make sure they're in the right units and plug them in. All right. So when we're doing these equations, I give you these. You don't have to memorize them. The first one up is percent mass over volume, percent M over V. All right. So it says take the grams of solute over milliliters of solution, and then times 100. Anything with percent, it's got this times 100. All right. So that one, a lot of times, is called percent by volume. And that's an unfortunate name because remember, volumes are not additive. So we never take milliliters of solute over milliliters of solution. We just can't do that. All right. It's not going to be reproducible. This grams over milliliters is used a lot. You have to be careful. Don't get it confused with, for instance, density. So the density would be the grams of solution over milliliters of solution. And there'd be no times 100 because it's not percent. So be careful. They're not the same. So grams of solute over milliliters total solution. Most everything has on the bottom the total solution. All right. Now, don't get this confused with percent by mass, or maybe they write it percent mass over mass. Both of these are equal. They're the same thing, and it's the grams of solute, what we're interested in, over the total grams of solution, and then times 100. So, whoops, off the screen, but times 100 because it says percent. All right. Now that one's easy enough. We use that a lot, but that percent mass over mass might not be scary enough. So grams of solute, grams of solution, times 100 may not be scary enough. The percents might be really small. And so we use that one a lot when we're talking about, maybe just normal concentrations or the amount of sugar that's in our food or something like that. But what if it's something that even a very small amount is dangerous, all right? So then we use this idea of PPT. Now PPT is part per thousand. Part per thousand. In other words, x over 1,000. Well, remember that percent is x over 100. So it's the same idea as the percent. So PPT, you'll take grams of solute over grams of solution, and then we'll multiply it by 1,000 instead of by 100. And this gives us a little more scary number. And so if you saw something that said 0.00001%, you'd be like, oh man, that's really low. I don't care. But it might be a dangerous amount. So we need a way of communicating this. Now, food, PPT works great. But drinking water, a lot of times, for instance, in Arkansas, we really worry about mercury in our drinking water. We want to have even lower concentrations. So ppm would be grams of solution over, backwards, grams of solute. What we're interested over grams of solution, the total, times m being a million 10 to the 6. All right. So now we're instead of multiplying by 100, we're multiplying by 10 to the 6. It makes it look a lot scarier. So then we have even ppb, part per billion. All right. It's x over a billion. So if I said something was 0.01% or 0.5 ppt or 20 ppm or 300 ppb and asked you which one was more concentrated, you might struggle with it because they're different units. You got to get them in the same unit. So instead, what I'm going to do is put them. This is percent, so it's 0.01 over 100. And PPT would be 0.5 over 1,000. ppm would be 20 over a million, 10 to the 6, right? And this would be 300 over 10 to the 9, which is billion. And I'm going to type them all in my calculator and figure out which one's the biggest. So let's see, this would be 1 times 10 to the minus 5th. This would be 5 times 10 to the minus 4th. This would be 2 times 10 to the minus 5th. This would be 3 times 10 to the minus 7. Remember this negative exponents? The smaller that negative is, the bigger the number is. So this one's actually my winner. This is the biggest, highest concentration. All right. So gotta be careful on these. They can be confusing. So there's two types of questions. One where they ask you this concept question, which one's bigger. But most commonly, they'll just give you how many grams of solution, and then you have to figure out how many. You'll have to figure out then what the ppm or ppb is. So these equations, they're all very similar, so they're not that difficult. All right. The one we use most commonly is this idea of molarity. So this capital M is moles over liters. Now, specifically, it's moles of solute over liters solution. That one we use all the time. We've used that in lab all the time. We might see something like this. And so anytime you see that capital M, moles over liters, we use molarity by far the greatest amount. Now, it's real common for us to give you a number in grams, and you have to find the molar mass to get the number of moles. So moles of solute over liter solution. Then we've got this idea of molality. And the problem with molality, we ran out of abbreviations, all right? So capital M is moles over liters. Remember, just moles is MOL, right? So all we could do drop was the E. There's no good abbreviation for molecule. A little m is meters, okay? So molality, they try to use italics M, but good luck writing that. So here's my capital M, my lowercase m, what am I doing? Italics M? I don't know. Good luck with that. But molality is weird because of its moles of solute, but the bottom part is kilograms of solvent. That's the weird part. Alright? Now notice molarity and molality, neither one's multiplied by 100. Alright? But this kilograms of solvent, that means they're measuring this differently. And why is this useful? Well, if I'm doing this on a large scale, where I have a really big container, like maybe the size of the room you're in, and let's draw my guy up here, and he's got a bucket, and he's going to throw that bucket in and dump in the solute, and then he needs to dump in the solvent. Now if he's got a big 55-gallon drum, he can measure how many the mass of the drum with the solvent in it, dump some out, put it back down, measure it, see how much he took out, and so he can real quickly measure how much he added down here. And then maybe this stirs The reaction takes place, and then they pump it out. There's some pipes or something. All right. So if we're doing large-scale stuff like this, the molality really comes in handy. Moles over kilograms. So that one is different than the others. All the rest of them have on the bottom liters or grams or milliliters of solution. All right. Now, one of the things that they hit you with in the lab a lot of times is you have to be careful that the grams of solution is the grams of the solute plus the grams of the solvent. It has both. All right. So terrible. All right. So you always have to be careful. Are they giving you the solute? Are they giving you the solvent? Or are they giving you the total solution? So you're looking for dissolved in. Those are your kind of keywords there. All right, so we're ready for this idea of dilutions. Now, it's unfortunate that we use this word dilution because if we make something more concentrated, it's the same math, it's just with different word for it, right? So a dilution, let's start with a container here, and let's say I have 0.2 moles of salt dissolved in this water, and I dump it into this big container. I won't even fill it up, it'll be way down here, right? So I dump it in here. How much salt is down here? Well, it's still that 0.2 moles. I didn't add any more salt. And then if I add a bunch more water and fill up this big container, as long as I don't add more salt, I still have the same salt. Now it'll be a new concentration. The moles that I started with will be equal to the moles that I end with. And that's the key to dilutions. And so we write M1V1 equals M2V2, really helpful equation for dilutions. Anytime you see diluted, we use this equation. But this is molarity, moles over liters. This is volume. Usually we use liters, or you can use both sides milliliters, it'll be fine. Well, what happens when I multiply these liters? I get moles equals moles. The moles we started with is equal to the moles we end with. These problems are nice and easy. We'll give you 3 out of the 4 variables. You solve the 4th. Man, super easy. They're great. Love those. M1V1 equals M2V2. Give me 100 of those on a problem. I'm testing. Take them all day.